طيب يعني عزيزم كاتتان باش بابتي أمرومان بريتيلا chapter 3 لا introduction to solid state physics بناونشاني X-ray diffraction وهذا chapter 3 X-ray diffractions. X-rays were discovered in 1895 by Röntgen. He found that a beam of high-speed electrons striking a metal target produced a new and extremely penetrating type of radiation. After a few months of Röntgen's discovery, the first medical X-rays pictures were taken. After several years, it became evident that X-rays were electromagnetic. X-rays are similar to light, but with extremely short wavelengths and greater penetrating power. This is a circuit diagram of producing X-rays. Here we have a high voltage for accelerating electrons, and these electrons, a beam of electrons from here produced, striking this target, which is made of tungsten, and this tungsten, and then from X-rays will be produced and comes out. And this is a three-dimensional circuit diagram of production of X-rays, clearly seen. This is the high voltage. Then from this circuit diagram, this is the voltmeter or ammeter reading the galvanometer. And then this is the instrument produces high-speed electrons striking the target and then emits X-ray diffraction. X-rays are electromagnetic waves with wavelengths in the range of 0.01 to 10 nanometer, frequency in the range 3 multiplied by 10 to 16 hertz to 3 by 10 to 19 hertz, which is the same order of magnitude as the atomic spacing in crystals. A particularly simple method of analyzing the scattering of X-rays from parallel crystal planes was proposed by Bragg in 1912. Conditions of producing X-rays. 3 things needed to create X-rays. 1, a source of electrons. 2, high voltage for accelerating the electrons to high speeds. 3, a target for accelerated electron to interact with. X-rays are produced when the free electrons cause energy to be released as they interact with the atomic particles in the target. And this is an X-ray spectrum after production. The graph shows the relative intensity of the emitted X-rays with wavelengths. This curve shows the X-ray spectrum when the accelerating voltage was 20 kilovolt, and this one for 30 kilovolt, and this one for 40 kilovolt, and this one for 50 kilovolt. Remember that 1 kilovolt means 1000 volt, so 30 kilovolt means 30,000 volts at the accelerating voltage. And this type of X-rays in German called Bremsstrahlung. X-ray spectrum from molybdenum. This graph shows the X-ray spectrum when used by bombarding the target made of the element molybdenum. And there are, it can be seen 2 peaks, K beta and K alpha. And these are the main characteristics of X-rays. The accelerating voltage was 35 kilovolt or 35,000 volt. Characteristic X-rays. X-rays production typically involve bombarding a metallic target in an X-ray tube with high-speed electrons, which have been accelerated by tens to hundreds of kilovolts of potential. The bombarding electrons can eject electrons from the inner shells of the atoms of the metal. Those vacancies will be quickly filled by electron dropping down from higher levels, emitting X-rays with sharply defined frequencies associated with the difference between the atomic energy levels of the target atoms. The frequencies of the characteristic X-rays can be predicted from the Bohr model. Moseley measured the frequencies of the characteristic X-rays from a large fraction of elements of the periodic table and produced a plot of them, which is now called a Moseley plot. Characteristic X-rays are used for the investigation of crystal structure by X-ray diffraction. Crystal lattice dimensions may be determined with the use of Bragg's law in a Bragg spectrometer. Characteristic X-rays are emitted from heavy elements when their electrons make transitions between the lower atomic energy levels. The characteristic X-rays emissions, which is shown as two sharp peaks in the illustration at left, occur when vacancies are produced in the n equal to 1 or K shell of the atom, and electron drop down from above to fill the gap. The X-rays produced by transition from n equal to 2 to n equal to 1 level are called K alpha X-rays, and those for the n equal to 3 to 1 transition are called K beta X-rays. Transitions to the level n is equal to 2 or L shell are designated as L X-rays. N equal to 3 to 2 is L alpha, n equal to 4 to 2 is L beta, etc. The continuous distribution of X-rays, which forms the base for the two sharp peaks at left, is called Bremsstrahlung radiation. X-rays are produced by bombarding a metal target, copper or tungsten, with electrons having energies of 50 to 100 kilovolt electron volt. The minimum continuous X-rays wavelength lambda minimum is found to depend only on the voltage V. All of the incident electrons' kinetic energy is converted to electromagnetic energy in the form of single X-ray photon. For this case, we have EV equal to HF equal to HC over lambda minimum. Then lambda minimum equal to HC divided by EV. Then lambda minimum equal to 6.63 multiplied by 10 to minus 34 multiplied by the speed of light, which is 3 multiplied by 10 to 8 divided by V, and multiplied by the charge of the electron. So the result will be lambda minimum 12.4 multiplied by 10 to minus 7 divided by V, the voltage. Example, a metal was bombarded with a high-speed electron accelerated through 30 kilovolt source. Calculate the minimum wavelength of the emitted X-ray. Lambda minimum is equal to 12.4 multiplied by 10 to minus 7 divided by V, and this will be substituting the values into the equation. Then the lambda minimum will be 4.1 multiplied by 10 to minus 11 meter, and which is equal to 0.41 angstrom. Angstrom is a small unit used for measuring length. Laue equation. Laue equation in crystallography, the Laue equation relates the incoming wave to the outgoing waves in the process of diffraction by a crystal lattice. They are named after physicist Max von Laue, 1879 to 1960. They reduced to Braggs law. It is enough to consider a row of atoms separated at a regular distance, as shown in the figure, and to consider the hypothesis that wavefront OP incident on the line of atom scattered cooperatively diffracts and produces another wavefront QR on the other side of the line, whose direction of propagation will have changed. And this diagram shows a plane incident on the atoms in the crystal lattices and then diffracted forward into another plane on the other side of the lattice. And the distance between the lattice or the atoms is A. Therefore, if the wavefront QR is observed, that is, if a cooperative scattering occurs, it is because the two component beams that define that front are in phase. In other words, the difference of path followed by the beams OQ and Q and PR between beams OQ and PR is an integer number m of wavelength lambda. So OQ minus PR equal to m lambda, and cosine V equal to OQ divided by A, and cosine mu equal to PR divided by A. It becomes A cosine V minus cosine mu all equal to m lambda. Therefore, we will get three equations accordingly. These three equations are mentioned here, related with A, B, and C multiplied by the brackets equal to m lambda, n lambda, and pH and p lambda respectively, where m, n, and p represent three integer numbers. These are the so-called Laue equation. So these three equations here are called Laue equation. Bragg diffraction. Two beams with identical wavelengths and phase approach a crystalline solid and are scattered of two different atoms within it. The lower beam traverses an extra length of 2d sine theta as shown in the graph. Constructive interference occurs when this length is equal to an integer multiple of wavelengths of the radiation. So this distance between two planes in the crystal is d, and the angle of incidence is theta. So, and the phase difference, the path difference between the two beams, one from the surface and one from the inner surface, d sine theta. So two distances measured. So n lambda equal to 2d sine theta, and this is called Bragg's law. So X-rays are scattered when it falls on a plane of crystal atoms. The equation of the scattering is called Bragg's law, as shown in the figure. This figure clearly shows how the Bragg's law, constructive interference when n lambda equal to 2d sine theta, which is called Bragg's law, and the two path differences. This is d sine theta and this is d sine theta. Sum of these two is equal to n lambda. Bragg's law is the foundation stone on which the X-ray diffraction stands. It holds same significance in crystal structure. It holds same significance in crystal structure determination as the Beer-Lambert law. The law was established by Bragg and his son in 1913 to explain the diffraction of X-rays from atomic planes of crystals of sodium chloride, zinc sulfate, and diamond. And a beam of X-rays incident to a crystal faces gets particularly scattered by the atoms of the crystal. And this law and the experiment of Bragg shows that the X-rays are waves because they exhibit diffraction, interference, and diffraction, interference also, and reflection and refraction. The fraction that is not scattered reaches the next atomic layer, where another part is scattered and remainder passes across to the next layer, and so on. As a result, the diffraction pattern is generated from the constructive and destructive interference of X-rays diffracted from each plane. A basic requirement for X-rays to diffract is that the sample exhibits crystallinity, and the spacing between the atomic layers must lie in the wavelength range of X-ray radiation. Thank you very much for watching and for listening. I hope this lecture was useful for you. Best regards.